So now let's discuss the Ethereum transaction fees. So I've already mentioned quite a few times gas. Gas is the equivalent of transaction fees in Ethereum. And for each opcode of the EVM that you would like to execute, there's a certain gas cost associated to it. There's basically a spreadsheet here, which we'll be looking at in a second. This gas limits the computational cost and certain DOS denial of service attacks, where otherwise somebody could issue a transaction that requires a lot of computation, such that the miners would not be able to basically mine a block because they would be blocked by doing this computation. So the miners choose transaction based on the gas price, but this is actually this is something that we'll discuss at the end of the slide of this lecture. And some opcodes might be overpriced, right? And they might be preferred by miners because they get paid quite well, while this is quite cheap for them to verify or execute. There's a maximum gas limit per transaction and per block, right? So the current gas limit is 12 million gas. So this is the maximum gas that you can include transactions within one block. So if your transaction requires more than 12 million gas, then it will not fit into an Ethereum block. Depending on how complex the smart contracts are that you develop, this might be actually quite an important limitation. So like in Bitcoin, all miners need to execute all transactions, right? You cannot not verify parts of the block and broadcast it, or you might run into troubles later on. And all miners need to store the code as well. But unlike Bitcoin, there's actually a gas limit that may halt execution abruptly. So in Bitcoin, you have this concept of either a transaction is valid or it's not valid. So if it's valid, it's executed. If it's not valid, it's not executed. And in Bitcoin, you have the block size limit, right? So your transaction size should not be bigger than the block size limit. Whereas in Ethereum, you have the block gas limit, which is just necessary due to the loops that are possible. So this is here these are here the gas costs. So you can see, for example, the opcode dup, right, requires a gas price of 3, for example. And you can see here there's some quite expensive opcodes like Easy Recover. That's a public key cryptography opcode, which requires quite some more gas to be executed. So and this might actually be updated over time. Yeah. So the as you know, the transaction format looks as the following. Looks like this here, and we have two fields which are quite important. It's the gas limit and the gas price. So if the gas limit times the gas price is bigger than the balance of your account, right, of this from address, then the execution is halted. And this basically means that the transaction is not able to complete until the gas limit, so the account would not be able to pay gas limit times gas price. Which makes sense. If it's not able to pay that, then the transaction is invalid by default and we should do it, right? Now, otherwise the balance of the account is updated on an ongoing basis, right? So you have here, this is the initial balance, and you basically subtract from it the value of a particular opcode based on the gas and the gas price, right? So and then here we can update the balance of the account that we sent some coins to, right? This is the to address here receives the value, so this is ether that is sent from the from address to the to address. Now, then we execute some code, right? And then we're gonna see if the code is executed, we have basically used up all the gas, and then we can see, do we have some unused gas? And if that's the case, then we're gonna add this back to the from account, right? So at the beginning, the whole amount is deducted, some amount is sent to the to address, and at the end we get back the unused gas that we haven't used. So the gas limit here is not always hit. and you get the remainder back. So the reason why we can't know exactly how much gas we're going to use, that's the halting problem. That's quite traditional in computer science. So we don't exactly know how long the smart contract will run, and that's why we have to approximate how much gas we're going to need. And that's basically the main motivation why we have this gas limit instead of a specific definition of how much this is going to cost. So there's also an out of gas exception. So if we if the remaining gas is 0 before termination, there will be an out of gas exception that's thrown. So the state reverts to the previous state, right? So so that the state is not modified, and the gas limit times the gas price is deducted to pay to miners, and this means basically everything is paid to the miners, but you don't get any execution, right? Which is quite bad. So we're gonna see here that the caller determines the sent gas. So let's look at the following example. So we have a contract A, which is a function small a, and we assert here that the message.gas is 100, right? So this means that somebody comes in and calls the function A and passes at least 100 gas, and that's the assert. Now we're gonna call the contract capital B, and in this contract capital B, we're gonna call the function small b, and we're going to pass this function small b 10 gas, right? So here now you have the second contract b with the function small b, and we're going to send it 100, we're gonna send it 10 gas. So what happens now is that here we're going to do the same. So we're going to call the contract C with a small c function. We're going to pass it 5 gas. So here 10 gas, and this is the final contract. So think for a second, look at this code, pause the video for a second, and think, what do you think is going to happen? Okay, so here we call basically the contract C, and we will see, okay, there's an assert 5 gas, there's a while loop. This while loop will never end, right? So it will necessarily end into an out of gas exception. So there will be an out of gas exception, and the whole program will return basically hello world, but not bonjour. Okay, so basically whatever happened here is reverted, and this will not change the state of the EVM. So how do you think miners order transactions in the block? So this is a small exercise. So think quickly for yourself, and then we can discuss this together. So if this is a block and there's a list of transactions in there, then these transactions, and this is the header, right? It's the block header with the previous timestamp, then the transactions are typically sorted according to the gas price. So this is the gas price sorting. So that is because if the gas price is higher, let's say here these pay 500 gigaway, and these pay 200, and they pay 100, and these guys maybe only pay 50, then obviously these transactions here are more lucrative to the miners, right? They're gonna receive these transaction fees, and this will yield a higher reward to them. Now, what turns out to be the truth is that only we have measured this empirically, so only at our time of the measurements, only 79% of the blocks are ordering the transactions according to the gas price, and the other blocks, we don't really know what's the strategy of the miner. Some blocks are actually empty. Some blocks are just ordered randomly. So it doesn't always happen that the incentive mechanisms are aligned as we think they would be, which is quite interesting. So if you have any ideas why they would be, we can. I would be happy if you discuss this or propose any ideas.